Okay, I want to go through chapter 2. Okay, so here's the main objectives. I'm going to talk about this concept of dimensions and dimensional analysis. Then we're going to look at the two unit systems of units that are common. System International, this is like the metric system. The USCS system is the English system, which is not nearly as common as the SI system. Okay, but we're going to look at that too because US still uses it. We're going to look at the idea of mass and weight and the differences. Then I'm going to go through and do some unit conversions. Okay, and there's some good examples in the textbook of these different topics. Okay, so what is a dimension? Basically, it's a variable used to specify some quantity. Okay, so there's two parts. Typically in math class, you just deal with numbers or often deal with numbers unless you have specific examples. Where we're dealing in engineering, we also have to know what the units are. Okay, so it's more than just a numerical value. There also has to be a unit associated with that. Okay, and of course, both parts are required for it to be useful. It's right. If you have a number 5, it's like, well, what is that? 5 what? Right? If it's the units could be feet, let's say, so 5 feet. The second part would be required, of course, to have it to be useful in a practical application. Okay, so just another piece of terminology. Dimensions are considered to be base or derived. Okay, and I'll show you what that means. Basically, and first I'll do that by talking about what a base dimension is. Okay, so a base dimension is basically a dimension you can't break it down any further. Okay, and what we're going to see is that when we talk about other dimensions, that they're just going to be essentially combinations of these. Okay, but these are the 7 base dimensions, and everything else we're talking about. If we're talking about velocity, acceleration, weight, these are all going to be based on these dimensions. Okay, all right. So first part of it is okay. So the rest of the other dimensions are all derived dimensions, and here's some examples of those. So area is derived dimension. Um, the velocity, force, voltage are all derived dimensions. And one of the things we want to look at is we want to do what's called dimensional analysis on equations that we develop just to see, if we want to verify that it's possible that they are valid equations. We want to make sure that whatever dimensions we have on the right hand side, and I'll take a look, I'll show you a couple of examples, are equal to whatever dimensions are on the left hand side. And so the right and left part of the equation are equal. So area, what does area have? Well, area is L represents length, right? So it's a length times a length. It could be inch times inch, inches squared, feet squared, meters squared, something of that sort, okay? So how you write it, and when we do our dimensional analysis, we just write it as L squared, okay? And remember, dimensional analysis is just going to be used for us to determine whether or not an equation is potentially valid, right? Okay. The next one is velocity. Now, velocity is just length, so right, distance, let's say, or length, divided by time. And one of the ways you can write is just like this. So time is the lowercase lowercase t is time, and so it's just like meters per second, feet per hour, miles per hour, something like that. Okay. And force is another example, and then voltage. So this one's a little more involved, but this is m mass length over time squared. Okay, so it's like it could be kilograms times meter divided by second squared is a common one. And this is a little bit more involved. Usually we don't go and drill down that far when we're talking about voltage, but voltage is also based on, this is another topic we have for later in the class. Force is just push or pull or weight. All right, weight is another force. But voltage is something we're going to handle later, and we're not going to drill down in this much detail of it. Okay, so continuing on. So the reason we identified just the the dimensions, is that, or the units, types of units, is that we want to make sure that the left side and the right side are correct. And like I said, I'll show you a couple of examples. Okay. So like here is, let's say we have an equation, we check it, and we find length on both sides of the equation. We know it's dimensionally consistent. Okay. And here's another one. Let's say we came out with mass on one side and time on the other. We know it's wrong. Okay. Even the power of that unit has to be the same, right? So this time it's length squared units on one side and length cubed on the other. Okay. So we use dimensional consistency to just, validate, is our equation that we came up with, is it possible that it's correct, right? Okay. So here's like an example. Here's our equation, and this is something we'll cover, later, the equation. You don't really need to know much about this now, except that this is straight line motion. So what this would tell you is that at some point in time, you're at some position, okay? If you're driving down the street in a car or something like that, or you're running or walking or something, you could, or, an aircraft's traveling through the, in a straight line fashion, traveling through the air. You could actually represent its position or with this equation. What this says is, where were you originally? How fast were you going, and how long were you going for? And this is our acceleration part of it, okay? How much were you accelerating? So with those three pieces of information, you can determine your location at any point in time, okay? And time would be divided by this, okay? But for our case, what we want to do is we want to look at just the units, okay? So this is a unit of length, this is a unit of length. This one should be a unit length too, right? It's going to be length over time times time, and time would cancel out. Of course, we have to have the right units in time, and that's length. And then this one, gravitational acceleration, just length. I'm sorry, yeah, length per time squared. Okay, so this is like meters per second squared, let's say, as an example in the SI system. And then time would square out, and so you have length here, length, length, and this is dimensionally equivalent. And this is just showing it in a little more detail. So D meaning distance or position. And then that's a unit of length, length. Here's length over time. The only thing is, I will say this example, there is, hold on a second. I'm going to go back and just show you this one thing that's a little bit different, okay? You see they use T for temperature here, uppercase. For this example, I actually got this from another place. They use uppercase T, okay? So just remember, this example is from a different text. Sometimes they'll use uppercase T. So in this case, uppercase T represents time, just for this example. In the book examples, you'll see they'll use lowercase t, right? So if you cancel out the times, then you'll find that it's just length on one side, L, L, L on the other, length on the other side, okay? So that's all this dimensional equivalency is meant to do, is just, hey, is this potentially a valid equation, okay? And we can see that, yeah, it could be, right? Because it's at least the dimensions equal. Okay. Another example is that you're going to see this in text is that, if you're looking for, like in this particular example, and you can work through it, but we can talk about this one, and you can see if you get the same results. And there's examples in the other examples in the text to look at. But just talking about this one, let's say we're looking for K, and we want to find out what K is, what its dimension is, okay? So what we want to do is essentially remove all these other dimensions from this side of the equation, right? So we could divide by everything over here. And if we move it over here, what we're going to find is that, this M is going to cancel out, one of the L's is going to cancel out from this one, and then time. So this one, your expectation would be that it's going to be length, because this one's gone. This is gone. It should come out to be length divided by time and times M, right? So it's L over T times M, okay? So you can work through this one and just do algebra on it, okay? Now this one's a little bit different, and one of the things you need to recognize here is that, and actually you could actually kind of jump to the conclusion here, but Uh, Everything inside of here, this is supposed to be unitless. Okay, so what you recognize, right off the bat, and we can verify it too, is that F really needs to be 1 over L. Okay, so that this has no units in here. So when you use any kind of trig function between the parens, it should be unitless. Okay, but if we take this, multiply both sides by uh, mass squared over here, and actually you can see that one of these m's just cancels out here, right? You can actually see that. So this just becomes 1 over m squared, right? Because this is just 1 over m cubed, right? So then you bring this over here, and then you'll find that on the left-hand side, there's no units. This side has no units, and when f is 1 over L, okay? All right. Okay. So we know this dimensions are typically expressed in units, right? And we have 2 common unit systems for this. Like I said previously, we have the metric system and the USCS system, right? And since we use this in the US, of course, we use them both in the US, it's often the case where we need to make conversions between the 2 unit systems. Okay, so unit conversions is an important aspect of engineering. Okay, so just in terms of just talking about the base units. Okay, so we'll talk about that. So these are all the base units are based on some standard. Okay, so so not that really that's that critical. I think there's something in the text about where each unit comes from, but it's easily looked up to find that. Not a critical part where the units come from, but recognize that they have to be based on some reproducible standard, right, for consistency. Okay. So here's some base dimensions and their SI units associated with them. Okay. So here's meter, and here's the symbols that are used for each of these. Okay. And we will be pretty much up in here. Amount of substances is, in chemistry, typically you'll see this, and then luminous intensity. These are common ones that we'll use in this class. Okay, these first 5. All right, so these are the base units, base quantities, and these are the base units associated with that. Right. Okay. Oh, so here are the base dimensions. Here's where they actually come from. Okay, so we have length, mass. This one I've heard it's changed recently, so you can look up and find out what it's changed to. But like I said, you really don't need to memorize these or anything. But recognize this: they have to be reproducible. Okay, so any of the world can reproduce this and maintain consistency. Like I said, this one's changed. Okay, so electric current, right? So this is actually just measuring the amount of electrons that go through a cross-sectional area, right? Okay, that amount of a substance, and then luminous intensity, right? Okay, so here we go. SI unit system, internationally accepted. Haven't adopted 100% here yet, so you'll see both still. All right, got to be familiar with both of them. All right. So here's some other derived units. Okay, and these are things that we'll talk about. Oh, Pascal is a important one for us. Of course, all of these are going to be something we'll take a look at. Coulomb is electrical charge, right? And this is just ampere, which I just mentioned previously. This is one of our base units. Right, here's our base unit, 1 ampere. So this is a quantity of charge per unit time, and when you multiply it times time, and then you have units of time, seconds, multiply times seconds, and this is quantity time per second, those cancel out, and then you're left with just electrical charge. Okay. All right, so one of the things we need to talk about is notation rules. There's rules associated with it. For consistent communication, we need to have the same, we need to be consistent in how we represent it, so there's no confusion and loss of information when we pass it on. All right, so first thing, never write units in plural. Don't do pounds is like lbs, right? You just do lb, right? Or kilograms, just do kg, right? Don't put a period after unit unless it's the end of the sentence, okay? That might confuse things. Don't invent your own units, so that's probably some good advice. All units are lowercase except in a few cases. So you're going to write the units as lowercase, all right? Multiple units should be separated with a dot, right? So if you have, let's say, actually, a good one is let's say newtons, kilogram times meters per second squared, okay? So kilogram meters, you put a dot between kilogram and meters. And one of the things you're going to notice is that there's a prefix, milli, that's often used in the SI system. And we don't want to confuse that with like meters, right? Because we're reusing it. So we need to be very clear of what's what. And a dot will help us do that, okay? So you'll see some examples as we go along. And all exponential powers applies to prefix also. So in this case, this is milliseconds, okay? Because we see there's no dots, not meter seconds squared. It's milliseconds then squared. So you could write it like this, because since there's no dot between it, you can recognize that, oh, this is milliseconds squared. So that's milliseconds are both m and s are squared, okay? Remember, this is for us in the engineering, right? Well, this is essentially the same thing as doing this. Writing it this way, right? This is more explicit. So you might, you want to write it like this. But if you follow the notation, the standard notation of the standard notation rules, you don't need that. Okay. Here's some more. Don't use compound prefixes. All right. Okay. So you don't use compound prefixes. Just to show you, I'll click to the next one. We're talking about prefixes. What we're really talking about is, using these symbols essentially to represent an order of magnitude. So instead of writing it in like scientific notation, if you had let's say 5 kilometers, you could use 5 km to represent kilometers, or you could write it as 5 times 10 to the 3 meters, right? Or you could write 5,000 meters, right? That would be the same thing. So for 5 kilometers, you could write 5 km, which is a nice short compact notation. You could write 5,000, 5000, or you could write 5 times 10 to the 3, right? That would be scientific notation. So when we're talking about prefixes, it's really what we're talking about. And recognize that these are only used with the SI system. Okay, I'll just take a step back. Okay, so put a space between numerical value and the unit. Okay, so don't write it right next to it. Put a space in there between it. So like 5 meters, 5 space meters, m. Okay. Do not put a space between the prefix and unit symbol. Okay, so if it was 5 kilometers, it'd be 5, put a space, km. Okay. And don't put prefixes in the denominator. Okay, so it's not a good practice, so you wouldn't put like millimeters necessarily in a denominator. Although, I'm sorry, yeah, sometimes you do, but a common practice is not to do that. Okay, so in general, we try to get rid of them in the denominator. So we show up as just like 5 meters, let's say, in the denominator. Okay, so here's the prefixes. Okay, so the English units. All right, so these are our base dimensions. Here's the units in the English system. Well, here's their comparable one, the SI system. So we have feet. Slug is mass. We commonly use kilograms, but there is one in the English system also. It's called the slug. Seconds, they're both the same. Temperature, Rankine and Kelvin. Ampere is the same. Mole is the same. They just write it differently, and candela is the same. Okay. So there's some conversions up in here we'll have to do. All right. Okay. Mass. So one of the key concepts we're going to look at in mechanics is this idea of mass, right? And it's the quantity of all matter, right? So when you're talking about weight, weight's different than mass, and that weight is dependent upon, where that mass is located. So if it's on like the surface of the earth, it has a certain weight. If it's off the surface a bit, that weight would actually change, right? Or if it's on another planet, on the moon or something, you have a different weight. Okay, but recognize that the mass, no matter where it is always the same. It's characteristic of the body, and the weight is characteristic of like where that body is located to some other mass that has some attraction. All right. So Newton's laws, we're going to talk about this. Three basic laws, and just to explain what each of these are. So if you have an object, and out in space is usually there's, it may be easier to visualize it, but you have an object. In that object, you launch a rocket out in space. It's out in space, long, far away from any planet. It's essentially going to keep going in the same direction until some other force like gravity or something else acts on it to push it off in a different direction. An object, let's say a car is rolling down a hill. Car, by your experience, it eventually stops, right? So if you start at the top of a hill and roll your car down a hill, it eventually stops. And the reason it stops, of course, is there are forces acting against that motion of the car, and friction, the wheels hit on the ground, and maybe some wind resistance. And eventually it would stop, okay? And that's your experience. But recognize that if there were no other forces acting against it, it would just keep going, all right? The second one is relationship between an object's mass and its acceleration. Okay, this is something that's treated a lot in engineering dynamics. We look at this equation quite often. But basic idea is that the force is directly related to the mass times acceleration. Now, this is a common equation for weight, right? So W equals mg when you're talking about weight, where g is gravitational acceleration toward the Earth, toward the center of the Earth. Okay, so this is a common one we'll have. And then the other one, where reactions equal and opposite reaction. Okay, you push against a wall, the wall pushes back with the same force. Okay, okay, that's good for now. So here's our weight. Weight is mg, and gravitation acceleration in terms of the SI system is 9.81 meters per second squared. So if you know the mass of an object, you multiply it times this, and then you can come up with its weight. And the units would be in newtons for the SI system. Okay. So if you want to figure out the mass from density, you'll have you start with density. So density is like mass per unit volume, and then you multiply it times its volume. So then you can figure out what the total mass is. Okay. So it could be water, it could be anything, steel, whatever object, sand, it doesn't really matter. Okay, what you recognize is that, yeah, if you have more of it, you're going to have a higher mass, right? Overall mass, which we'd expect, right? Because you have more of something, you're going to have a higher weight because the mass would have to increase. So continuing on with this, it depends upon, how do you calculate weight. You need to it's really going to be dependent upon what the mass, the units of the mass are given. Is it kilograms, slugs, or is it this other thing called pound mass? Okay. If it's kilograms, G is just 9.81 meters per second squared. If it's slugs, so if it's in terms of slug, then you're going to have to use 32.2 feet per second squared, right? And the last one is if it's given in pound mass. So this is another one. In this class, these are more common. Kilograms going to be the most common, but in this case you have this like conversion factor that you have to account for. So here's like our G, the same as this, but then you have to divide it by 32.2, and these are the units, so that when you do the calculation here, your units come up to be pound force. Okay, so this is another way to represent it. What you'll recognize is that on Earth, in terms of the number, 32.2, these just numerically cancel out. The only thing that really is left over is the units that come from here. So if you're on the surface of the Earth and you're given a mass, let's say 10 pounds mass, you know that the weight is going to be 10 pounds, okay, on the surface of the Earth. Okay. So unit conversions, we'll take a look at this. So it's often the case where we want to convert from one base unit to, I'm sorry, not base unit, but one unit to another unit, or unit system, one unit system to another unit system. Okay. So basic process, you write down the units, determine what units you have to make the conversion to, and typically that's what's asked for. Multiply by any given conversion factors, draw through line through canceled units, perform the calculations, and then for us, we're going to represent our final result in three significant figures to be covered later. Okay, so we'll talk about that. All right. So like here's an example. In this case, you would need to cross out the units, but you could see that millimeters would cross out here, meters would cross out here. Say we're trying to convert from millimeters to kilometers, and then you're going to be left over with just kilometers be the only unit left. Okay. And here's another example. This is a little better. So let's say cars rate in feet per hour, and let's say this is what you're given. You're given in terms of miles per hour. So we have here's our problem that specifies what our rate is, and then in this one we need a conversion factor, miles to feet, right? Because we're given in miles, and now we want to make that conversion. Okay. So the question becomes is it 5280 feet per mile or 1 mile per feet? Okay. And really it depends upon what you're trying to convert to, right? Because this is just one. This is a quantity of one. So when you multiply any number times one, you still have that same number, right? And this is also one. It's just two different representations of one with the goal of just changing our units. Okay. All right. So this is like an intermediate step. You could do this if you want. But the basic idea is that you have miles per hour and feet per mile. So they're just showing you in terms of the units what it would come up to be. So the miles would cancel, and then you're left with just feet per hour. So here's the actual problem, working through it. Here's my initial rate, 72 miles per hour. Here's my conversion factor. Miles cancel out, and now we have feet per hour. So you just do this multiplication, and this is just, of course, 1 hour times 1, and then you have 380,160 feet per hour. Okay, so this is a kind of a simple example, but it shows you kind of the main steps. You may or may not have to do this step. It's up to you, but it's good to, this is a good detailed example. Okay, so basic idea, for this chapter, there's, I'll work through some other examples and additional videos as we go along in the class, but we have two different unit systems. Both, of course, have the same, they're just different unit systems. They have the same base units, the 7 base units. Okay, so dimensional analysis, if we want to make sure that we use that, if we want to determine if it's possible, right? Okay, and it's one of the things we're going to look at, in this chapter, and we're always going to pay attention to it in the end, but we won't do dimensional analysis beyond like this chapter. Derived units come from base units, of course, and then mass is if some quantity that doesn't change, characteristic of that object. And then we use conversion factors, of course, to change our units. And that is really about it.